So, okay, very good. Let's first start with somebody said battery. And battery, these circuit elements connect to concepts. And that concept is EMF. Right? EMF, electromotive force. That's the thing that gives energy to the system. A battery has an EMF in it. They also have that small thing called an internal resistance. That's why batteries heat up if their current is too big. Like if you take a wire and connect one end of the battery to another, that's kind of dangerous. Don't do that. You'll cause the battery to blow up. And no, it won't blow up in an interesting way. It will just overheat and kind of pop open and spit gooey stuff on the table.
Acid.
Yeah, it's like an acid. What?
Resistance.
What? Oh, it's because there is an internal resistance inside the battery. And remember the equation for power, which is I squared R? When you connect, so it's a really tiny resistance. So when you connect one end of the battery to the other, you get a massive current. And then the massive current results in power being given to that resistor.
We're recording. The world just knows that's happening.
Right, so yeah, that internal resistance, with the current, gets a massive amount of heat. That heat changes the chemistry inside the battery and makes it explode. How do you what? It's pretty much a simple, like sort of just a chemical reaction. And you remember you did like a standard, let's say, decoupler, like this is A, this is B, they come together to make C. And then C has a lower energy state than A and B, right? That's why they come together, because A and B are up here. When they combine, they drop energy, and that's C. Well, when they drop energy, that energy goes into electrons that get released. You get the basic idea? Okay, that's how pretty much most batteries work. Now, a rechargeable battery, you pick A, B, and C such that if I inject an electron with energy, I will break C back into A and B. And that's it. So whether that's lead acid, whether that's nickel cadmium, whether that's nickel metal hydride, whether that's nickel ion, silver sulfate, whatever the other things, like all these things reactions, it's all the same. A plus B equals C, boom, and that gives you energy. Then energy plus C gives you A and B. Thank you very much. Sarah, Wants, Paul.
What the hell?
So yeah, on that note, I'll move on. All right, so batteries give us an EMF, right? So what else is in a circuit that we're going to deal with? Okay, good. We'll have capacitors, and then that relates to what concept? What do you call the measurement for capacitor? It's capacitance. Capacitance. Capacitance on the circuit. All right. What is the unit? Oh, of course. What is the unit of EMF? Yeah, it's in volts. Right. This is connected to that concept that we talked about called electric potential. Right. And then capacitance is in what units? Farads. Right? And this is actually related to electric fields, because what's inside of a capacitor? Yeah, electric fields. That's what stores the charges, right? The charges stay there because of the electric field. What else have we dealt with in circuits? Good. Resistors. And of course, that is in what units? Okay, and that's this R, but it's in ohms, right? And that's good. And then anything else? Yeah, we have this concept called current. Oh yeah, with I'll do that in a second. And current is of course I. That's in what units?
Amps.
Good, amps. And yeah, that's pretty much it too. So we have these things. This E, this I, this R, those are most of our circuits, and then sometimes instead of R, we can swap this C. Okay, and then what concept is connected to this E, I, and R? What marries these three concepts together? Numbers, numbers.
What marries these three concepts together? A priest.
Whose law binds these three things? Ohm's law, right? That connects those three things together. It allows us to see their relationship.
Aw, how cute.
Okay, so then, of course, what equations, well, let me go ahead and say, okay, so we have these three things connected together, right, and then we have to include other concepts, right, along with these. Remember that this is joules per coulomb. Current is, an amp is a coulomb per second. Now, ohms is whatever, it's just volts per amp. So I don't know, I guess you can say that's joules per coulomb over coulombs per second. And then that means, I don't know, you get joule seconds per coulomb squared. I don't know, it's not nice. These things make more sense. And hopefully you realize when we combine these two things, what do we get? Yeah, we get power. P equals IV, right? Of course, power is in what? What are you doing? Hello. Right? And then don't forget we have other equations, right? By using Ohm's law, we can say V squared over R. We can also say I squared R. And then how do we deal with capacitors? What do we have? What equation deals with that, basically? The behavior of the capacitor? Yeah, C equals Q over V. The nature, or kind of the characteristics of the capacitor, is C is K E0 A over D. Those are the two equations that relate to that. With current, we have what law connects to current, or what rule? The junction rule. The loop rule relates to what thing in this triangle?
Wait, what are the loop rules and the junction rules?
This is the loop rule. What does the loop rule say? Okay, you could say that. The sum of any path through an electric circuit has to be 0. Right? And then so the sum of the voltage is going to be 0 when you go through the circuit. Kind of a side little note is that parallel has the same voltage. So if you have two things that are in parallel, they must have the same voltage. Now the junction rule, right, says the total current is constant, which means throughout the circuit, the total amount of current never changes, right? And then the junction rule also says that things in series have the same current. So the loop rule helps us see that things that are in parallel have the same voltage. The junction rule helps us see that things that are in series have the same current. And of course, finally, the last thing has to deal with the addition of resistors and capacitors. When you add, so then these things come together in this strange sort of thing, right? Resistors, when you add in series, what do? Yeah, you just add them. And when you add in parallel, then you add the inverse. And of course, remember with capacitors, it's the opposite. So capacitors, when you add in parallel, you just add them. And then add in series, it's inverse. And that is pretty much everything in chapter 24. Yes. Good. Not nice. I was just being silly. Because that doesn't cancel into anything cool. It's just this ugly thing. Oh yeah, just as a further side note, remember that resistance is rho L over A. For a resistor, resistance is rho L over A. This is that concept called resistivity. That's where I said, you know, silver is the least resistivity, it's the best conductor, but we don't use silver for wires because it also corrodes very easily.
Is rho a constant?
Yes, it is. It's a constant per material. So, like for different metals, you get different values. Okay? When you're talking about capacitors, if you add parallel, you just add them. If you add series, then you inverse. Yeah. So capacitors in parallel, you just add them. Capacitors in series, you inverse. I mean, nothing that I've said here is new. This is all just those two things, real quick, we'll recap. So, the best way to recap is let's do a problem. So let's see. These will be resistors. This will be 4. That'll be 4. This will be 6. That'll be 3. And this will be 9. This will be 3. I don't like that. I'm going to do that. I'm going to do. So this is 12, and this is 4.
Wait, what are these numbers?
That's the resistances.
Oh, I'm sorry. That's a 9. Why is this easier?
And this is 14. Nah, it's not easy. This is 7. And then this is 7 volts. So, figure out the current and the voltage on every resistor. Go. Feel free to talk with each other. I will give you 9 minutes.
Okay, so there are 2 equations.
What's that? Oh, good idea.
I